All right, so the plan for today, we just kind of did the quick attendance review, and we're going to cover section 2.1. This is probably a lot of this material in chapter 2 is going to be familiar from your previous coursework, either Math 90 with us or with another elementary algebra, Algebra 1, something like that, in high school or at another college. So this should be somewhat review, but we're going through this material. We're especially going to take a bit of time to go through section 2.1 because it's so foundational for the rest of the stuff we're going to do in the course. So I did check WebAssign this morning, and it looks like only about half the class has signed up for that. So make sure that you get signed up for WebAssign. Again, the instructions are on the Blackboard site, and I'll go through in the supplement. I'll post a supplement. I'll probably post some additional course information later today, and then section 2.2 tomorrow, most likely. But make sure you get logged on to WebAssign. And there's a 2-week free trial with that. So even if you don't have, your course materials yet, if you're waiting for financial aid to come in, no problem. You can log on with that free trial while all those logistics get sorted out. Just this morning, I posted a chapter 1 review homework. Should be a pretty quick homework to work through. It's mostly just a review of some arithmetic operations, things like adding, subtracting fractions, those kind of things. I would recommend doing most of chapter 1 without a calculator just for practice, mainly because these same ideas are going to apply to some of the algebra stuff that we're going to talk about in the course. And a calculator will be a little less helpful on those. So I would recommend for this chapter 1 review, try doing, say, at least half the problems without a calculator, doing some of them by hand, adding some fractions by hand, that kind of thing, just to get back in the practice of that. So when we get to things like, say, rational expressions, where we're trying to add fractions that have variables in them, we kind of remember the strategy. Okay, so that is the plan for the rest of this week for today's class and the supplemental video.
Can I ask a question real quick?
Yeah, sure.
So I'm signed on to Synage, whatever, but it's asking me for a class code. I
Yeah,
have my access code, but I don't know where to find it. I'm sorry if you said it, I missed it. I'm sorry.
no, that's fine. Yeah, the class key is, let me bring up my other screen here. Yeah, so if you're in Blackboard, if you go to course documents and WebAssign registration instructions, the class key is up here. This ccac.cc.pa space 4 numbers, space 4 numbers.
I
Yeah.
put that in, but it didn't work. I'm gonna try again though. Thank you.
Okay, yeah, make sure you include the spaces and this prefix, the ccac.cc.pa. If that doesn't work, if you can send me a screenshot, and then we can kind of investigate it.
Okay, thank you.
Yep, sure thing. Okay, any other questions before we move on? All right, and the quote of the day today is from Greek philosopher Epictetus. This is a very loose translation, but something along the lines of conceit of knowledge gets in the way of learning. Or in other words, when we feel like we know everything about a certain topic, we're probably not going to keep updating our knowledge base and including more information as it becomes available. And we're kind of in an interesting age these days that for most of human history, probably the main issue with trying to understand something was getting enough information. And today we're kind of on the flip side of that. We have so much information. You go and Google anything you want, and you're going to come up with 1,000 web pages all trying to tell you what they think about it. We have to be curators of information more than generators of information. So how do we decide what information should be trusted, what's high quality information, and what's not? A lot of people will use what I think is a cop out, and they'll just say, "Oh, just listen to expert sources, either expert people or expert, highly reputable web pages, but that just kicks the can because you have to define expert then. And if you really dig down and question people about it, most of the times their definition of expert is either people who agree with what I think is true or people who have some, credential or something like that. And you can very quickly find counterexamples where, well, what about this person who has that credential who you think is, a complete goof? Oh, well, that doesn't count, right? So it becomes a no true Scotsman fallacy issue. Um, so anyway, I think this is one of the big challenges today is weeding through all of the information we have to try to figure out what's good information, reliable, valid, truthful, however you might want to say it, and what's not. Okay, so moving into chapter 2. Again, with this being a hybrid class, our meeting time is 1 hour, and then we have typically I'll post a supplemental video for the extra class time that'll kind of supplement what we go through in class. So class itself is going to be fairly fast paced because we want to make good use of this hour. But obviously, if I'm going too quickly, if you're missing anything, definitely stop me, ask questions. We certainly have time to go back and review something or answer any questions. So starting with 2.1, using a general strategy to solve linear equations, we're going to start off with some terminology and properties. Again, this might be more familiar to you, might be a little less familiar to you. We're just going through all of this. Everybody's on the same page, and we have a really solid footing in this important material. So the first important note is the difference between an equation or maybe an inequality versus an expression. So if I just have something like, say, 3x plus 2, this is an expression. It's a combination of mathematical operations. By this, we mean take some variable x, multiply it by 3, add 2, and that's what we have. I could maybe evaluate this expression for, say, x equals 1. And remember, a variable is just a placeholder. It's just something that I can substitute in a number later on. I can pick a different number and substitute it in whenever I would like. So if I evaluate this for x equals 1, I get 3 times 1 plus 2. I do multiplication before addition. So that's 3 plus 2 equals 5. So I can evaluate expressions. I can manipulate them using things like maybe a distributive property, stuff like that. So this is an expression. In a sense, it expresses an idea. An equation, though, is a claim. It's a claim like 3x plus 2 equals, x minus 1, something like that. It's either a claim or maybe you would say an assertion. It's a statement that something is true. It's a claim, an assertion, a statement that this expression and this expression are equivalent, are logically equivalent, or represent the same number. Now, of course, if I plug in kind of an arbitrarily chosen value of x, typically these two sides of this equation are not going to balance, as we sometimes say. Typically, those two sides of the equation are not going to represent the same number. If I chose x equals 1, I see on the left side, that's the same expression as over here. I get 5 on the left side, but for x equals 1, I get 1 minus 1 is 0 on the right side. Well, those are clearly not equal. So typically with an equation, the typical case is that there's a particular value of x, maybe one value of x, or maybe in other contexts, maybe 2 or 3 values of x, that when I substitute it into the expression on the left and that same value into the expression on the right, it gives me the same number on both sides. And then typically, all the rest of the x's don't work that way. If I substitute them in, I'll get different numbers on the left and the right. There are some exceptions to that, and we'll see some of those later on in this lecture even, but that's kind of the typical case. The most important rule for equations is this idea of balancing the equation. So if I do make an assertion like this, if I say for the value of x that I'm interested in, it's true that the expression 3x plus 2 and the expression x minus 1 represent the same number for the value of x that I'm interested in. What value of x is that? Well, I suppose I could solve this equation by just guessing a bunch of values of x, but that's quite inefficient. And maybe if my value for x is like 2, maybe I could find it reasonably quickly. But if it's like, you know, 17.318, are you ever going to guess that one, right? Probably not. So I want to develop a strategy to solve equations algorithmically. I want a process that I can go through to find the solution of an equation, not just the guess and check kind of method. And again, the most important idea is that our equation has to balance. So there's this kind of sense in which we have like a scales, and we start off by saying, our 3x plus 2 and our x minus 1, they balance. They at the end of this, whatever value of x that I find, these ought to like weigh the same. They ought to be the same number. Now I can manipulate my equation by changing one side of the equation. So if I like subtract 2 over here, if I imagine taking 2 pounds of weight off the left side, well, if I just subtract 2 off the left side to get rid of that, maybe this plus 2 is causing me a little bit of annoyance at the moment, so I want to get rid of it. If I just subtract 2 from one side, well, I'm off balance. I've got to do that to the other side as well to maintain that equilibrium. You could think of this in terms of weight on scales. You could think of it in terms of, say, finances. If any of you are interested in accounting, you need to keep your ledger balanced. So if you put something in the debits, it's got to come out of the credits as well. And so there's multiple different analogies you can use here. But the most important idea is if we do something to one side of the equation, we also have to do it to the other side of the equation to maintain that sense of balance. And as we kind of, demonstrated above, we can look at a particular value for the variable and ask whether it's a solution to an equation. So I have an equation here. I have an assertion that the expression 5x minus 4 is equal to the expression 10x minus 7 for some value of x, for the value of x that I'm interested in. And my question is that value of x 3/5? Well, I can plug it in. And when I plug in, and I typically put an X or a question mark here, because I'm not sure whether this is equal or not. So this is a proposal. It might be true, but I'm not sure. So we're going to check. So I usually don't like to just put an equals there because that might be mistaken as me making another assertion. In this case, I would be making an assertion that I'm not sure if it's true. But this 5 over 5 divides out. I get 3 minus 4 is -1 on the left side. Is that equal to what's on the right side? 10 over 5. The 5 divides out and leaves me with a factor of 2. 2 times 3 is 6. Minus 7, -1. So yes, it is a solution. We can say that x equals 3/5 is a solution to this equation. So what's our goal in solving an equation? Roughly speaking, the goal in solving the equation is to isolate the variable. In other words, to get the variable on one side of the equal sign and all of the other numbers on the other side of the equal sign, and probably ideally we should simplify all of those numbers. there is a little notation, a little technicality. If I were to end up with something like this, say x equals 3/5, some people would look at this and say, well, this is still an equation because I have two sides, two expressions. Now, they're quite simple expressions. One expression is just x, and the other expression is just the number 3/5. They're very simple expressions, but I still have two expressions where I'm asserting a relationship between them. So some people would say, well, this is still an equation. If we want to represent the solution, if I want to communicate to you that 3/5 is the solution, I maybe would want to say something like the solution set is curly braces, 3/5, and curly braces. So some people would say that this is the proper way to communicate a solution, and that if I just wrote that, that in their view, that's not a solution, that's just another equation. Now, personally, I think this goes way too far into the semantics for most things we're going to discuss, but it's worth pointing out because there are situations, and we will see them in this course, where we will be very worried about the set of solutions. So this is an important idea in some cases. I think it's a bit overkill for say linear equations though. So I think for something like this, it's a tool, but it's kind of like a sledgehammer. You don't use a sledgehammer to pound in a little nail to hang a picture. So we don't really need this whole idea of solution set notation and all of that at this point, but just be aware that that is out there. Okay, so any questions to this point?
No.
All right, so moving into one-step equations, I just noticed I didn't have my chat window popped up. So since I hide all the Zoom meeting controls, I just popped that up so I can see if anybody posts in chat. Okay, so moving on to one-step equations. So again, I have my idea of the two sides being balanced and then doing an operation to both sides. And the idea of a one-step equation is that I should be able to solve these types of equations using one equation operation, one kind of arithmetic operation done to both sides of the equation. So if I'm looking at an equation like this, r plus 1/3 equals 1/2, this would be a one-step equation. What would be the one step that I would want to do? What operation would I want to apply to both sides of the equation to work my way towards a solution? Any ideas?
Subtract the 1/3 from the left side and well, both sides.
Exactly, yeah. So the main thing is we want to isolate that variable. We have a plus 1/3 attached to our r. We want to get rid of it. So the driving force is I want to subtract the 1/3 from the left side. And then I also need to maintain balance in my equation. So I also need to subtract 1/3 from the right side. On the left side, this nets out just an r. My plus 1/3 minus 1/3 goes away. And on the right side, I have 1/2 minus 1/3. At this point, I've isolated the variable. I probably should look at that right-hand side, subtract those two fractions. In this case, well, 1/2, I know that that's 3/6. And 1/3, I know that that is 2/6. 3/6 minus 2/6 is 1/6. Now, one really important idea in mathematics is I can take a specific example like this and think about how to solve it. And if this was an Algebra 1 course, this is kind of review at this point for us, but if it was an Algebra 1 course, we would go through, 6 or 8 problems like this and look at all different kind of variations of this type of problem and similar problems that are somewhat like it. But here we just have one as a demonstration. And then what I would say is, after going through, if you imagine going through 6 or 8 pretty similar problems, you might start to extract a more fundamental principle. You might start to extract a rule or an algorithm that you can say, okay, whenever I see an equation that fits into this mold, variable plus or minus number equals number. Whenever I see something that fits into that mold, I know exactly what step to apply without even knowing what those two numbers are. So if I have an equation that fits into the mold, say x plus a equals b, where a and b are some numbers, a could even be a negative number. So this might look like x minus 3 equals 2. But here we're thinking of x as the variable that we want to solve for, and a and b are two numbers. Well, x plus a equals b, I solve that by subtracting a from both sides, and I get x equals b minus a. So we have now a general method to solve this one-step equation. If I have x plus a equals b, I know that my solution looks like x equals b minus a. That's like a formula that solves this kind of equation. And then, I would put in my particular values of a and b. Might have to still do some arithmetic simplification on the right-hand side, but my algebra is already figured out for this type of problem. This is an important idea that will come up against a couple of times in the course. So you might remember, say, the quadratic formula. It's a similar idea to this. Or we'll see later in today's lecture that we'll have a process for solving general linear equations. So we'll have a way to go about solving more complicated linear equations. We could actually come up with a formula for solving a general linear equation, but it kind of turns out that that formula is, messy enough that it's better for us just to remember the process and go through that instead of trying to remember the formula like this one. Okay, let's look at another example. Solve this equation. 4m minus 1 minus 3m plus 7 equals 5. Now we would still call this a one-step equation, even though it looks a lot more complicated than what's above. And one important thing that we always want to do in linear equations, but also most of the time across math, if we're looking to solve an equation, we probably want to take each side and simplify it as much as possible. If I have like terms I can combine together, I probably want to combine them together. If I have things with parentheses where I can use a distributive property and multiply them out, I probably want to do that. There are a few cases where maybe that's not the best strategy, but most of the time it is. So I do see I have some like terms on the left side here. Let me put those terms together. So I have a 4m minus 3m. The minus sign has to come along with it. And then minus 1 plus 7 equals 5. The right side, nothing we can do with that. But I do notice that 4m and 3m, those are like terms. They have the same variable or variables to the same power. So I have 4m's minus 3m's. That gives me 1m, or we just write that as m. So typically we would write 1m just as m. We just don't write the 1. Not that it's really wrong to write the 1. It's just, it will be very unusual to see it written that way. And then I have minus 1 plus 7. Well, that nets out to a plus 6. So we can see after some simplification, after I take my left side, that expression, and simplify it, and if I needed to, take my right side, that expression, and simplify it, a lot of times things get a lot simpler to deal with. That's why we call it simplifying. And I recognize that this falls into this category up here, m plus 6 equals 5. So m equals 5 minus 6, or negative 1. oftentimes I'll kind of chain together equalities instead of rewriting them like this, just because it's a little more efficient. Because if thing A equals thing B and thing A equals thing C, then thing B equals thing C as well. They're all equal to one another, the transitive property of equality. So after all is said and done, we see that m equals -1 is the value of that variable that we're looking for. It's the value of m that, when substituted in to both sides of this equation, results in an equation where both sides are the same number. And in fact, for examples like this one, if I chose any other value to substitute in, if I chose m equals -2 or +10, those would not be solutions. There are scenarios where we might have 2 or 3 solutions to an equation, or maybe even infinitely many solutions to an equation. Or there are scenarios we might have no solutions to an equation. But for problems like this one, we have unique solutions. So this is going to be the one and only value of m that, when substituted in, results in a true statement. Okay, let's look at this next one. Again, this looks very complicated, but if I just take it one step at a time, it's not too bad. Well, I see that I have an equal sign in the middle here. So I have two expressions I'm claiming are equal to one another. These are both complicated expressions. I should probably try to simplify them first. I can go through my order of operations. I know that I have to do parentheses before anything else. I'll use my distributive law on all of these parentheses. And that'll break everything apart. I'll be able to identify my like terms and combine them together. So for instance, I have 5x plus 5 times 2 is 10. And then plus x minus 10 just copies down. That's the left side. And the right side, I distribute, I get 3x minus 21 minus 3x. And I got to be careful here. This minus 3 goes onto the x, and it multiplies the -1. So -3 times -1 is +3. I can combine like terms on the left side. I see 5x plus x is 6x, and plus 10 minus 10 actually cancels. So my left side all reduces down to just 6x. That got a lot simpler. My right side, 3x minus 3x actually cancels, so I'm left with no x's on the right side. And then minus 21 plus 3 ends up being minus 18. So I now have an equivalent equation. These two equations, the first one and the second one, what I mean by an equivalent equation is that they will be true for exactly the same values of x, value or values of x. So I've come up with a second equation that's much easier to deal with than the first equation, but that has exactly the same solution set. And that's the whole idea of doing these equation solving steps. And so if 6x is -18, we know that we need to divide both sides by 6 to get x equals -3. And again, in an Algebra 1 course, we would go through a half a dozen examples like this, starting with much easier looking examples, working up to something like this, and we would realize that there's an underlying pattern here. If I have an equation that looks like ax equals b, where x is the variable I want to solve for, and a is not equal to 0, I can solve this as x equals b divided by a. So if I recognize that an equation is in this form, rather than the, say, x plus a equals b form, if it's the a times x equals b form, then I know that this is what the solution is going to look like, or I know that the solution method is going to be divide by a. Any questions so far? I know that we are moving, at a pretty good pace here. I'm hoping that this is, review for most folks, and that most folks just need to maybe dust off the cobwebs a little bit. But if you do have questions, definitely ask. Okay, so now we're going to try to combine these previous ideas. So the previous ideas were one-step equations because I only needed to do one. Yes, yeah. So the Zoom lecture is being recorded, and I'll have it posted on YouTube, typically within a day or two after class. Yeah, so you'll be able to come back and review it if you'd like to. Absolutely. Yep, sure. So these one-step equations, they're one step because it only requires one equation solving step, doing something to both sides of the equation to get the solution. It might require, some additional uh, manipulation of the expressions, but notice that going from here to here, we didn't actually do an equation solving step. All we did is simplify the expression on the left-hand side and separately simplify the expression on the right-hand side. That had really nothing to do with this being an equation. If I had just given you this expression and this expression as two expressions to simplify, you'd have done the same work. This was the equation solving step where I did something to both sides of the equation. And then I had one kind of finishing up step where I said, okay, -18/6, I want to simplify that. That simplifies to -3. So again, that's just a simplifying an expression. So we really only had one equation solving step here. Similarly, up here, we had one equation solving step and then a little bit of simplification. Now we're looking at equations where we have more than one equation solving step. So these are multi-step equations, or in this case, two-step equations. And again, here we might be able to intuitively figure out what the steps are and write a formula like we did up here. But sometimes writing out a formula, the formula is just messy enough that, if I try to write out the formula, I'm probably going to get something backwards somewhere. Maybe it's better to just remember the strategy. Sometimes it's better to remember the formula. Sometimes it's better to remember the strategy. And in this case, we're going to remember the strategy. So we have basically a four-step process. Different people break it up different ways, but I like this way of breaking it up. The first thing we do is we try to get to a standard form. We try to get to a form that's recognizable, say like this, right? So if I have a big complicated equation like this, I want to take each of those sides of the equation, each of those expressions individually, and simplify them down as much as I can. If I'm dealing with a linear equation, I can always simplify down to ax plus b on one side and cx plus d on the other side for some numbers a, b, c, and d. I can always get down to these four terms, the two terms on the left, the two terms on the right. If you're not able to get down to these four terms, either you're maybe missing the ability to say combine a couple of like terms, maybe you overlooked one of the like terms, or maybe this is not a linear equation. Like if I had an x squared floating around, that's not a linear equation. If I had an x squared, I wouldn't be able to guarantee I could get down to something that looks like this with four terms, but that wouldn't be a linear equation, so it wouldn't fit this mold. But for any linear equation, we can get down to this form. We call this standard form. The idea of standard form is an important idea. It's a way that it's kind of a goal that we can shoot for that helps kind of kick off our pattern recognition. A lot of math is about pattern recognition. You say, oh, I've seen this before. I've solved similar equations to this before, 20 times. I know how to do this. So once you get here, you kind of know where you're going. Now, getting to this point might require some different strategies, right? Maybe sometimes you need to distribute, maybe other times you need to, well, I don't have any other good examples, but, or what here, maybe other times you need to just combine some like terms. So you need a more flexible strategy to get to this point. But once you get to this point, then we can just kind of follow this pattern. So once we get to standard form, the next thing we do is we get the variables on one side. I prefer to get the variables all on the side with the largest coefficient. So note that here I set this up so that A is bigger than or equal to C. I put my large coefficient of X on the left side. And if I want to get my X's on the left side, that means I'm going to have to subtract CX from both sides. So I need to subtract CX from the right side and from the left side. That gets my variables on one side. And then I want to get my constants on the other side. Remember, I want to isolate the variable. So I start by isolating the variable term. On the left, this gives me A minus C times X. And on the right, I have D minus B. But now I kind of recognize this. This is just some number. A minus C is just some number. Let's call it K times X. And D minus B is some number. Let's call it J. K times X equals J. Well, I know how to solve this. That looks just like that pattern, right? Number times X equals number. So now I see that X equals J over K, where J is D minus B and K is A minus C, right? So we could develop a formula. We could say that X equals, what would it be? D minus B over A minus C. That's going to be hard to remember though, right? I have two negative signs, so if I get either the numerator or the denominator backwards, I get the wrong answer. I need to remember where the A, B, C, and D go. So I probably don't want to remember this formula, but I could come up with it if I needed to. But I first isolated the variable term by subtracting to get all the variables on one side and subtracting again to get all of the constants on the other side. And then I isolated the variable itself by dividing by the coefficient. Those were really my two equation solving steps. Or if you wanted to break it into three, if you wanted to get the variables on one side first, simplify, then get the constants on the other side, simplify, then divide, you could do it in three equation solving steps. There's nothing the matter with that. Now, one thing that we haven't done yet that's very important. So we've simplified, we've used equation solving steps. We have a solution that we think is the solution, but we ought to get in the practice of checking our solution. So here I have three examples where I have hypothetical solutions, and we're just going to practice checking solutions a little bit. So pretend that, you had gotten this equation given to you, you had gone through some steps, you had gotten down to A equals -1, and you want to know if that's correct. Well, instead of just circling it and moving on to the next problem and maybe getting that one incorrect, let's check it. How can I check it? Well, my claim is, the thing that I'm asserting here is that when I substitute -1 in for the variable A in this original equation, the two sides of the equation should simplify down to the same number. Well, let's see if that works. That's the claim I'm making. Let me check and see if that is actually true. Right. I don't want to become conceited in my knowledge and disappoint Mr. Epictetus. On the left side, I have 3 times -1 is -3 minus 1 is -4. Is that equal to 4 times -1 is -4? Yeah, that looks good. I came up with a solution of a equals -1, and I verified that that is a solution. So again, suppose that you were given this equation to solve, you went through some steps, you did some simplification, you ended up with the solution a equals -6/7. Your claim is that if I substitute -6/7 in for a everywhere in this original equation, all the way at the beginning, then the number on the left should equal the number on the right. Does that happen? So is this true? Well, if I put everything in terms of sevenths, I get 3 times -6 is -18 over 7 minus 7/7. Is that equal to, I got rid of my extra space so you can see everything, and now I need it back. Is that equal to -60 over 7 plus 35 over 7? I just multiplied my 5 by 7 over 7, and same with my -1. Or this would be -18 minus 7 is -25 over 7. Is that equal to, well, -60 plus 35? I think that is also -25 over 7. So yes, we have verified that our claim is true. We were claiming that a equals -6/7. We were either claiming that you can view it as -6/7 being a solution, or we're claiming that these two equations are equivalent, and we verified that that's true. And we could do this a third time. We, again, have an equation. Suppose we went through some algebra, some steps to solve this. We ended up with the solution x equals 3. We're claiming that that's the solution. Is it actually? 5 times 3 plus 7, is that equal to 16 times 3 minus 9? So that's 15 plus 7. I think that is 22. Is that equal to, well, 16 times 3 is 48, minus 9 is 39. And in this case, when I substitute in 3 for x, I get an equation that is not true. So something somewhere went wrong. X equals 3 is not a valid solution. I should go back and check my work. So this is a very important part of this process. Is we get a solution, we're making a claim, we most of the time can check that claim, and in fact most of the time we can check that claim much more easily than we can come to that claim. In other words, plugging back in to check the solution typically takes much less time and effort than it took to generate that solution. So if I took 3 minutes to generate the solution and it takes 20 seconds to check it, why not check it, right? Why would I potentially waste 3 minutes of work? Maybe I missed a negative sign somewhere or something by getting something wrong, when I could spend a proportionately little amount of time checking it. As kind of a side note, I think there were quite a few folks interested in computer science and those kind of fields. There's an interesting classification system for problems having to do with like the P versus NP conjecture and so on. And roughly what it comes, one way of characterizing it is, for some problems like this, if I tell you, if I make a claim, this is the solution, it's easier for you to check whether that's the solution than just generating the solution from scratch yourself. And there are other problems where that's not true. So this is an easier problem in that sense, that if I tell you, hey, I think this is the solution, it's easier for you to check it than to generate this solution yourself and check it that way. There are problems like the traveling salesman problem where I say, you have to go to these 10 places. What's the shortest path? If you come to me and say, this is the shortest possible path, the only way that I can check that is actually to redo the problem and check all of the possible paths and verify that I got the same answer you did. At least that's the only way we know of at the moment. So interesting little computer science tidbit. But this particular problem that we're studying is one of the nice problems where if you're given a solution, it's much easier to check it than to derive the solution from scratch. Okay, so let's work on solving some equations. So here I have a general linear equation. Actually, let me change this around a little bit. Yeah, I actually want to change both of these. No, this one's okay. All right. I had a detail that I was not too happy with in this first equation. I think the second one is fine. Okay, so let's look at this first equation. Again, I have a linear equation, but it's not in that standard form. It's not number times x plus number on both sides. So I want to start working with it. I want to start massaging the two sides to get it into that standard form that I can then do the isolating the variable term, isolating the variable, simplifying, and checking. So doing all of those steps. So start on the left side, I'll distribute first. I get 10x minus 5 plus 7. And that's going to be equal to, on the right side, distributing 2x plus 6 plus 10x. On the left side, I can simplify a little more. I get 10x plus 2 minus 5 plus 7 is 2. And on the right side, I can combine my 2x plus 10x to make a 12x plus 6. And maybe at this point, I'll kind of switch these around. I'll make it 12x plus 6 equals 10x plus 2. If I have a equals b, I can switch that to b equals a. That's no problem. So that puts my bigger coefficient on the left side. The coefficient is the number that multiplies x. Now I want to get my variable term isolated. I want number times x equals number. That's my end goal. I'll subtract 10x off of both sides. That gets rid of the x's on the right side and puts all of the x's onto the left side. But now I have this plus 6 that's kind of intermingling with my x's on the left side. I want to get rid of it off the left side. So I do a minus 6 and a minus 6. That gets my constants off of the left side. So I now have 12x minus 10x on the left side equals, and I have 2 minus 6 on the right side. Or I have 2x equals negative 4. So this was my first equation solving step. But now I'm down to another equation. It's simpler. It's one of my one-step equations. I can do one more equation solving step, simplify and check, and get my answer. I can divide by 2 on both sides. So x equals negative 4 over 2 is negative 2. So this was my second equation solving step. If you wanted to break this first step into 2 different steps, no problem. You can do that. You could get the x's on one side first, simplify everything, then get the numbers on the other side, simplify everything, then divide. No problem with doing it that way. And then let's check. I think x equals -2, but let's go back to the original equation all the way at the beginning, plug x equals -2 in, and see if that works. Again, I'll put a little question mark above my equals because I'm checking. I haven't checked that it works already. And on my left side, if I start inside my parentheses, I get 2 times -2 is -4 minus 1 is -5. And on my right side, I get 2 times +1, -2 plus 3 is 1, minus 20. My left side can simplify a little more. I get -25 plus 7. Is that equal to 2 minus 20? -25 plus 7 is -18. Is that equal to -18? Yes, it is. So I have checked that x equals 2 is the correct solution. Any questions so far? All right, I think we will skip this next one just for time considerations. And we'll talk about an equation that has a fraction in it. So here I have the equation 3/4 times 4m minus 8 plus 7 equals 4 minus 2m. So when I have a fraction in an equation, oftentimes the first thing I want to do is clear the fraction. So one thing I can do here is I can say, well, if I have one or more fractions in an equation, I can look for the least common denominator for all of those fractions. And I could just multiply both sides of the equation by that least common denominator, distribute everything carefully, and I'll end up with all my fractions going away, and I'll just end up with I'll end up with a linear equation in this form, but where a, b, c, and d are integers instead of having some fractions. So that's certainly a useful thing to do in many cases, and in the next problem, we'll actually do that. But here I actually notice something, right? One point that I want to make is if we have a general pattern, sometimes it benefits us to just ask, okay, like if I deviate from this, is there a reason to deviate from this? Is there a special case? Is there some little trick that I can apply? Something that I actually notice here is this fraction isn't all that bad, because if I were to just distribute it, I see that that over 4 is going to divide out the 4 and the 4m, and it's going to divide out a factor of the 8, which is 4 times 2. Should I go through and multiply by 4, make all of my integer numbers 4 times as large, and then just have bigger numbers to work with and have a lot of simplification to do on the back end? Well, in this case, I can choose to deviate from that strategy a little bit, simply because I recognized something that just works out nicely. It just happens to work out nicely in this case, that when I distribute 3/4 to 4m, the 4's divide out, minus 3/4 times 8, the factor of 4 and the 8 divides out and leaves me with a factor of 2, plus 7 equals 4 minus 2m. Or this leaves me just with 3m, 3/4 times 4m, minus 3 times 2 is 6, plus 7 equals 4 minus 2m. Or I have 3m plus 1 equals, we can say -2m plus 4. We could write it that way if we really wanted to force the issue and make it look exactly like our pattern. Ax plus b equals cx plus d. here our variable is m instead of x, but it's the same pattern. So now I recognize my equation in standard form. I go through my problem solving steps. Or my equation solving steps. I get the variables on one side. Since I have a minus 2m on the right, I have to add 2m to both sides. I get the constants. Did I say variables on the right? Variables on the left. Can't get my left from my right figured out apparently. Variables on the left. And then I get my constants on the right by subtracting 1 from both sides. So this gets rid of that constant on the left, puts all my constants on the right. And the previous step is going to get rid of my variable on the right, put all the variables on the left. That gives me 5m, 3m plus 2m equals 4 minus 1 is 3. And now I divide by 5 on both sides. M equals 3/5. And ideally, we would then go back and check that this is indeed a solution to the original equation. I'm not going to do that here, but because I want to get to this last one, but ideally we would do that. As a side note, we have this last little topic in classifying types of equations. I'll push that to the supplemental video recording. So this problem that we do will be the last problem for today. So one thing that that we probably should realize is that decimals and fractions are kind of qualitatively the same thing. They're both represent something to do with parts of a whole. So here I have an equation with decimals in it. I might not want to deal with these decimals. It's a little harder to deal with operations with decimals. I might forget to bring the decimal along with me and so on. So I can clear decimals in a similar way that I can clear fractions. I could have cleared fractions up here, but again, I chose not to because I saw a little trick that I could do that let me avoid that. I don't see such a trick here, so let me clear the decimal, so to speak. I note that everywhere I see a decimal, it only has one decimal place to the right. So if I multiply 2.6 by 10, I get 26, a whole number. If I multiply 1.1 by 10, I get 11, a whole number. So if I were to multiply this equation on both sides by 10, I would get 10 times 2.6w minus 50 equals 10 times 1.1w plus 10. And now I distribute. I have to be careful to distribute properly so that my factor of 10 hits all of the terms throughout both sides of the equation. But 10 times 2.6 is 26 times w minus 10 times 50 is 500 equals 10 times 1.1 is 11 w plus 10 times 10 is 100. And now I have a nicer looking equation with just whole numbers or integers that I can deal with. I can get my variables on the left side and my constants on the right side. 26w minus 11w gives me, what is that? 15w equals 100 plus 500 is 600. Divide through. W is 600 over 15. I do see that there's a factor of 3 in both. That's 200 over 5. I know that 5 times 20 is 100, so 5 times 40 should be 200. And then again, ideally, I would go back and check this, but we are out of time.